Okay, so next speaker is Sarah Dean from Cornell University, and she will talk about learning dynamics from bilinear observations.
Cool. All right, just testing my microphone. Sounds good. Cool. And I've got a clock there, which I noticed is a minute or two fast, so I should finish hopefully on time so we get to break. So yeah, today I'm going to talk about learning dynamics from bilinear observations. Actually, the title's not so descriptive. Half the talk I'm going to motivate why are we thinking about this problem, what are bilinear optimizations, and I'm mostly going to be focusing on this intersection of kind of learning and control, learning and dynamics, with an eye towards what are we doing with machine learning, maybe the downstream optimization problems, but it won't so much be the focus of my talk, although hopefully some of you can get interested in these problems and work on them with me. So this research and a lot of my research in general is motivated by the existence of large-scale automated systems that are powered by machine learning. And this means a variety of things, right? I think maybe in the more controls community, we think of things like chemical plants, robotics, these physical, built, engineered systems that we kind of design carefully, and that now we have this opportunity to use machine learning to improve them in some way, to model something that physics kind of failed us for. But I actually think where machine learning is maybe most clearly used and most clearly having impacts are automated systems that are not so much built and engineered. Well, sorry, they are built and engineered. All aspects of them are not built and engineered. Many aspects are us, people, the economy, right? We have social media, we have online shopping, we have online news systems. A lot of this content is served to us through algorithms, right? These automated systems. And those algorithms are powered through learning from behavioral data. So this is kind of the application that I have in mind for studying the different questions that I study. So let's just set up the problem, like what is machine learning and what happens when we use it in these settings. In general, machine learning is kind of the way we go from training data to a model. And a model is something that will take an observation about the world and then make a prediction, right? So for example, I go online, I'm browsing a bunch of news websites, I have these historical interactions that are built up in my cookies and various data sources about my behaviors, and there are models that take this data and predict new interactions, right? They say, these are the articles that I think Sarah will click on. So more generally, right, the observations and this training data come from some environment, come from some world. They might come from my browsing behavior, your browsing behavior, more global browsing behavior, right, depending on the setting. But this is not really the end of the question. We don't just predict this for fun, write it down, test our accuracy later, and say, it's so cool, we could be accurate, right? Actually, the reason we make these predictions is in order to serve content, to show me ads that I'm going to click on, to suggest articles that are most relevant to me, to help me sort through which news of the day should I actually take a look at. And so there we go from predictions actually to actions. And then I've drawn this feedback loop all the way around because our actions are actually impacting this environment that our data came from, right? They're changing the content that I see. And because of that, this turns into a feedback loop, right? Feedback arises because our actions are impacting the world. So this is not just a closed decision pipeline, there's actually this process happening. And I think for the first part of the talk, I'll focus on what are the implications of this and why does this matter? And then I also want to point out that when you have feedback loops like this, when this is the actual data generating process in some sense, the training data that you have to even learn models in the first place is correlated because it's collected from these settings where you have dynamics and feedback. So whether it's the impact of an action on the world itself or also just the temporal dynamics of the world and the way that it evolves over time. Both of these things can affect the learning process. Okay, so there's two things that I want to talk about today. And I would love to take questions during the talk, so if anything I say isn't clear or you want more details, please raise your hand and feel free to interrupt. I've tried to design this talk so that I'll have plenty of time for interaction. So first I'm going to talk about kind of motivating the setting. So what happens when we have simple models of impact or simple models of dynamics for personalization using machine learning. How does this change the status quo? And then I'm going to talk now about, it's nice to hypothesize a model and say what happens, but what's actually happening? Are we influenced by the news articles that were recommended? Really, how would we learn that from data? And so then I'll talk about some pretty fresh work on learning dynamics from bilinear observations that's directly motivated by that. Okay, so here I'm going to set up our problem setting, and then I'll talk about kind of two different implications, assimilation dynamics and harm. So our setting is going to be preference dynamics or opinion dynamics. These are the way that a person's preferences, which govern their behaviors, may be influenced or changed through interactions with a system. So we have, just drawing my diagram of me browsing the internet. I'm on my laptop clicking different links. What's happening in the background is, links are populated on a web page according to some recommender policy, which chooses what content to surface. And my expressed preferences through clicking, through scrolling, through linger time are recorded by that system and fed back into the policy, right? And so to set up some math, I'm going to call this recommended content, I'm going to call an input or an action, and I'll use u as a variable. So like recommended content at time t is u sub t. I am behaving according to some preference state or some internal state, which I'm going to call x sub t, which is generally unknown and hidden. And the preferences that I express are measurements, they're outputs, they're something observable. And so I'll call those, I think, observations or measurements y sub t. Okay, so kind of general setting, I've just introduced a little bit of basic dynamical systems notation to recommendations. What else can we say here? So one thing that will be consistent throughout my talk is the bilinear observation model. So we'll say that the measured outputs, the observations, my behaviors, are the result of a bilinear interaction between my preference and the content, or the recommendation, right? So it's an inner product between x and u. Hard to point this. Plus some noise. Actually, I think I'm going to change that to v sub t later, but that's fine. Plus some noise. And why are we using this? I mean, so a couple of reasons. One is it's kind of the simplest thing that makes sense. What would be simpler than this bilinear model would be a pure linear model, right? It would say it's the sum of a linear function of my state and the input. That's pure linear, but that just doesn't make sense when you're talking about personalization and reacting to content. Because it means like the magnitude, the effect of my preference is not interacting with the qualities of the recommendation. They're just like two independent terms that you would sum. So it really doesn't make sense. There needs to be some model of interaction here, right? And this is also, the kind of simple model that underlies all factorization-based methods. So in the simplest case of matrix factorization, which has powered a lot of recommendation, maybe a little bit less so these days, but it's still a very powerful technique, which models, given lots of users and content. So the famous example would be the Netflix prize where we had movies and user ratings. A very effective model for solving this problem is to factorize this matrix into a factor corresponding to user preferences and a factor corresponding to attributes of movies. And in this case, right, we end up with each predicted rating is an inner product of the user preference and the attributes of the movie, right? So just a little motivation on why we think about bilinear models. Yeah, question?
Why should x and u have the same dimension?
That's a good question. So in the matrix factorization setting?
No, the dynamics.
Yeah, okay, so yeah, right. In the dynamic setting, they do because of this assumption. In the matrix factorization setting, they're both hidden, like there's a hidden dimension, and otherwise they can be determined from the data for any given dimension. In the control setting, which let me go back to, the preference state is hidden, so maybe we can say like we want to be agnostic to its dimension, But you're right in pointing out that as soon as we make this bilinear assumption, we're now saying the inputs are of the same dimension. And if the inputs are observed, so if we know something about the recommended content, then we're assuming something about the preference. That's true. So in the second part of my talk, when I'm going to discuss learning, I'll introduce a matrix that transforms dimensions, so you don't have to make this assumption anymore. And that allows for a lot of flexibility. So for example, you could do something like model inputs as like one hot encoding vector, so every piece of content is just totally distinct from other pieces of content. And then the relationship between content would be modeled in some unknown matrix that would transform U before doing an inner product. So I will model that in the second half. For now, we're going to keep sticking with this simple case. Yeah.
It's a big departure from the usual sort of dynamic modeling process where things are linear. And here you're deliberately breaking that linearity with a bilinear assumption because your state is obviously influenced by the input.
Yeah.
And there is a strong reason for that. I mean, bilinearity is something that is quite common in engineering circles, but we deliberately try to move away from it because we don't know what to do with them.
Yes.
But in your case, that is a necessary thing.
Yeah, my argument is this is essentially necessary. That like if you're modeling response to something, there is a bilinearity, at least in the observation. So in the dynamics, later on we'll do linear dynamics because that's the case that's easy to deal with. But in the observation, I think this is almost necessary. And I will say like this kind of observation model is usually, like if we treat X as fixed, so we don't model dynamic, we don't have any changing state, it's just an unknown parameter of my preference, then this actually would be like linear regression, and then it's not so bad. It's just when you allow this to change that it's really a bilinear setting. Yeah. Okay. So just like I just alluded to, I guess, unlike a lot of recommendation settings where we model these parameters of a user's preference as fixed, I want to think of this as something that changes, where the state is actually evolving over time. Okay, and I'm going to actually have it evolve depending both on the previous state as well as the recommendation and possibly some noise. So these are kind of my settings, my measurement equation and my dynamics equation. And now I just want to go through some examples, so some work that I've done in this setting and the implications thereof. For these examples, I've looked at preferences and recommendations, right, which lie in the same dimensional space, and actually, I'm going to say the preferences lie on this unit sphere, and for simplicity, I'll also say the recommendations do. So really, direction is encoding everything here. So what's a very simple example of preference dynamics? One is assimilation, where your interests become more similar to content that is recommended. So your interest is proportional to like your previous preference plus some scalar eta sub t times the recommendation that was made. Right? And so proportional to, because we might want to normalize everything to keep it norm 1. This effectively says, well, let's go through an example. So let's say I'm listening to music. This gray line here is my initial preference. And this red line represents the playlist that Spotify generated for me. And if you look at this model, and let's say my preference is related to, my behavior, my positive behavior is Y. So how long I listen to the generated playlist, for example. If I look at this inner product, it's going to be positive, so it's a good sign. My preference is fairly aligned with the recommended playlist, and so I'm happy. And so under assimilation, it doesn't actually matter if I was happy or not, but I was. Under assimilation, I'm actually going to like this even more. So next time I would like the same playlist even more, so my preference kind of rotates towards the recommendation. That's what assimilation dynamics mean. Another example is biased assimilation, right? So this is a little bit simplistic. It sort of says, I can recommend a playlist anywhere on this circle, and you might hate it. It might be totally against your interests, but next time I recommend it, you would like it a little bit more, right? That's what assimilation says. It says you kind of are always agreeing. Not so realistic. So one other possibility to consider is bias assimilation. Here, we would say the interest update is actually proportional to the affinity, where I'm going to use the word affinity to just refer to this inner product. So it's like the rating, it's the amount of time I listen to something. And very similar equation. The only difference is that the coefficient on the recommendation has this inner product. And this inner product can be positive or negative, which means that the update can be towards the recommendation if I really liked it. So in this example we just went through, I would have sort of the same type of update. I would rotate my preference towards the playlist. In magnitude, actually depending on how much I liked it, so how quickly would I rotate towards it. But let's say actually I recommend some playlists that I really don't like and I did not enjoy it, then my preference, starting gray, would rotate away from that. I hate it even more now. Right? So this is a biased assimilation. And bias assimilation and assimilation are kind of like more general concepts in these equations in like opinion dynamics literature. These particular models and the particular bias assimilation model was proposed by some folks in 2019 to model opinion dynamics. And the prior work in this space has thought less about personalization and just more about how opinions in a population might evolve. And so if I'm motivating that by recommendations, I'm going to say global recommendations. So, suppose everybody has the same news homepage, we all are exposed to the same content, there's no personalization, and let's say that our opinions or our preferences update according to either of these two models. When you make global recommendations like this, these two models are actually quite different. The assimilation dynamics, right? Let's say I have lots of people who have lots of different opinions or preferences, then under a global recommendation scheme, we would end up converging to homogenized preferences. Obviously, this is simplified, and there's lots of other effects, but holding everything else constant, ignoring any other noise or diversity, this model is saying that you move towards homogeneity. Right? Everybody becomes the same, no matter what they initially thought. Whereas the bias assimilation model, people still converge, but they converge to one of two poles. So it actually leads to polarization. So some people who started with certain opinions become more magnified, more aligned with each other, and opposite another group of people. And in this particular model, it's exactly two. There's exactly two poles that you would converge to. So that's sort of the prior work view of this in terms of opinion dynamics. What about personalized recommendations? Is this like, can we use this to understand or explain claims that social media and recommender systems are enforcing polarization because of echo chambers or something? So in the personalized recommendation setting, actually the story is a little bit different. So regardless of whether you have biased assimilation, so either normal assimilation or bias assimilation, in either case, as long as you make a recommendation that is somewhat aligned with preferences, you make relatively good recommendations, people don't hate what you're showing them, then if you, for simplicity, let's say make a fixed recommendation to somebody for all time, then their preference will, at time t, is the combination of their initial preference with a positive but decreasing coefficient and the recommendation that you're making with a with a coefficient increasing in magnitude. In the bias assimilation case, it may be in the negative direction. Somebody may be really hating what you keep recommending them over and over again. But as long as you start relatively close to their initial preference, you will converge just to the recommendation. So there's not so much of a difference here. There's a slight difference, but not so much of a difference. And so if you believe that personalized recommendations work even a little bit, then this type of modeling suggests that actually it's not clear that biased assimilation in particular is what would matter for polarization. At least recommendations are not that pathway. So what are the implications of some of this modeling? I'm not actually going to go into the details here, but you can look at a paper, which I'll have on the last slide, that was at EC, Economics and Computation. So one implication actually is, if you believe in these dynamics, it's not necessary to identify preferences to make high affinity recommendations, to make recommendations that people will engage with highly. Why? Because this model says that people like things more if you show it to them enough. So you just have to find something that people kind of like, and then they'll actually adapt to you. So we might think that these algorithms are smart, but maybe not really. We're just kind of behaving in a certain way in response. If you believe the model, sure. The second implication is like relating to what happens at a population level. So at a population level, we wouldn't necessarily see polarization, but we could see some kind of preference collapse. So, if users are only recommended, certain types of content, and all of their preferences move towards those frequently recommended content, we would start out with, a much more diverse set of preferences and result in kind of a less diverse set of overall preferences, let's say. So this could matter if you don't have a diversity of content to recommend, right? That's maybe one thing to worry about, but not so much polarization. And then the third thing is that if you did, want to combat, this kind of collapse phenomenon, you wanted to say, let's keep everybody's preferences the same. I don't want to manipulate what people like. It is possible to do that with recommendations by randomizing your recommendations appropriately. You can sort of ensure that individuals kind of maintain their initial preference. Unfortunately, the algorithm that does this could also shift people's preferences arbitrarily depending on how you set it up. So it's not a purely, pure-hearted setting. And this, of course, only holds under this model, which I think is probably not exactly how people behave or people's preferences evolve. But it helps us think through some of these questions. Okay. Ooh. Cool. Oh, actually, let me refresh this page. I had some Unicode characters that I think I fixed. Okay, awesome. So what else can we say? Like, if we have preference dynamics like this, what other implications should we be worried about? How should we change the practice of designing recommendation systems, of surfacing content for individuals? So one that I thought about recently is harm. So what does it mean for recommendations to be harmful to their users? So I'm going to think of the most basic definition possible. There's definitely a lot of other things you could talk about, but one is just that there's some content out there which is harmful. It's something that is against terms of service to expose to users. We don't really want to be encouraging people to find this content, whether it's hate speech, whether it's conspiracy theories, something that we consider bad, and something that's so bad that we wouldn't actually choose to recommend it. And so, okay, I didn't totally fix my Unicode problems, but that's fine. The simple choice model here is that, given a recommendation, a user will select the recommendation with some probability that's proportional to their affinity. So if they like the recommendation you surface, they will, go ahead and say that's a good playlist, I'll listen to it. Otherwise, the user is apt to choose from the whole global universe of other content, to look elsewhere for something to consume based on their affinity. So again, based on how much they would like that content, how much they're drawn to it. Right? And so in this example, in the absence of recommendation, I'm trying to illustrate a simple case of user preference in black, a bunch of different songs. We're going to go lighthearted with harm here. A bunch of different songs, also embedded in the same two-dimensional space. And one of these songs is harmful. In this case, let's just say this is a song that gets stuck in your head. If you listen to it, you really regret it afterwards. And so you really do not want to be recommended it. Like, you don't want to listen to this song. Right? And so, however, in the absence of recommendation, what's the chance that you listen to each of these songs? Well, there's some chance you listen to this red song, because you kind of like it. Like, you just, you might click on it, right, by accident. Let's say we don't actually know before we listen to it that it's going to get stuck in our head like this. So we make the mistake, right? But if we make a recommendation, we can actually change the probability that we click on each of these songs. So if we recommend this song over here, then we increase the chance that the user clicks on that song, and we can proportionally decrease the chance that they click on any of the other songs, because they're more likely to accept a recommendation if they like the recommendation. And the way I've drawn this is actually very symmetric. I could also recommend this Unicode error here song, and that would lead to these click probabilities, right? So it would up this chance, and then similarly decrease the chance of all other ones. Okay, so I have a claim up there that I haven't said yet. My question is, let's just say I'm trying to design this for a user. I have their best interest in mind. I know that if they click on this song, they're going to regret it. What should I recommend to them? Clearly, I shouldn't recommend that song. Should I recommend, this song, this song, this song? Does it matter? Right. So everything here is proportional to affinity, and they accept the recommendation before choosing to look elsewhere. So if I can maximize the chance that somebody accepts my recommendation, I'll minimize the chance they look elsewhere and stumble upon this horrible song, right? And so if you don't think about any preference dynamics, you don't think about anything else, you can make the argument saying that actually minimizing harm in this case is equivalent to maximizing engagement. We just want to make recommendations that users are most likely to click on, because our recommendations, of course, this is like a benevolent overlord setting where we know what harm is, we know to filter it out, we never recommend something harmful, and so as long as we maximize engagement on the non-harmful sets that we recommend, we're minimizing the chance somebody stumbles upon something they'll regret. Right? So this is great, and actually, good news for all social media companies, because that's what they're doing, and it's actually for everybody's benefit, right? Nothing could go wrong. However, maybe that's not the case. One way to maybe destroy this story is with preference dynamics. If we have something like assimilation, even bias assimilation, where after a recommendation, our preference moves in the direction of that recommendation, the story is a little different. So on the previous slide, I was kind of showing you these two equivalent songs, where is this? Here and here, right? Which are, roughly equivalent. They both kind of have high chance of clicks, and they both have relatively low chance of harm. But in the following time step, thinking about the future, if my preferences change, then there is a difference between these two, right? This song, I become less interested in things like the harmful song, whereas this one, I become more interested. And so if you look at the kind of future click probabilities, this is a much better choice than this, right? So the takeaway is that if we think about harm in an admittedly simplified way, but also kind of, if this doesn't work in the simple case, then it probably won't work in the complicated case either. If you think about harm in this way, in the absence of preference dynamics, there's, status quo is great. We should just do what we're already doing. But if there are preference dynamics, then basically we should be careful, and we should think about this and take into account the downstream effects when we make recommendations. This is the topic of a paper that will be at KDD later this summer. Actually solving this problem is kind of challenging. It requires a bunch more modeling assumptions and some non-convex optimizations, which is kind of interesting. It does, again, assume essentially an assimilation-like model of preference change, right? So something quite simple. All right.
You said you wanted to be interactive.
Yes, yes.
Okay. So does it mean that if you go back to your picture, right? So red is R, and everything that goes towards that is really bad. So if you think about drugs, right? Okay, then don't drink a glass of wine, because then you go towards that. So that's mean you become polarized. The best thing is just to, become extreme on the other end.
Yeah, well, yeah, so I agree with your critique, and right, this would say things like, right, also like this poor musician, whatever, like, we like this musician, and yet we don't want to recommend them to people. I think there's a difference between, and obviously the musician example, this is something to think hard about if you're Spotify, but there is a difference between like pushing things on somebody and having them available. So like, right, like drinking wine at dinner is great, but getting like blasted with advertisements for Budweiser constantly, I don't know if that's actually good. Like maybe that is something that large-scale algorithmic systems should think about. So I partially agree with what you're saying, and I don't think this is the end of the story. But there is an argument that social media is amplifying things in some way that are undesirable. Is it just that we don't know, like, is it just that we don't know something is harmful? Like, we didn't realize the song was bad, so oops, Facebook recommended it? Or is it really that even when Facebook can rule out content that it does not want to surface or recommend or amplify, something about the dynamics of social media are still encouraging users to fall into these holes? I think there's an argument that something there is happening. But yeah, I don't really want nanny state Facebook either, so yeah.
So I had a question about what happens if, this might not be in the purview of the study, but if you have a content that is on your feed that is recommended versus that is just because you're following somebody, for instance, and because they post something, it just pops up. Have users been informed that this is recommended content versus this is because you're following it? Has that changed their preferences in terms of how they would react to?
Yeah, that's a good question. So I think the move is honestly like away. So there's certainly a difference between you follow this person and it's on your newsfeed, and like you don't follow this person, it's on your newsfeed. But even when you follow people and their recommendations and their content is on your newsfeed, there's still a recommendation algorithm that decided to show that content at a certain position. I would almost argue like everything is recommendation based, and there might be some effect of what's the source, like what's the pool of possible recommendations to make. And that is somewhat influenced by like user follow choices, and that actually does have I think a large effect in some of the like real world empirical analyses of like what types of information people see. That pool does have an effect. But I'd argue that like actually the movement of social media is sort of away from that kind of thing, like with short video, like all TikTok stuff. It's much more algorithmically curated. This is sort of like it's easier to hide ads when you get control over everything, right?
Yes. Sorry, quick follow-up. Just to add on to that, I guess I agree with you. I think most of social media now doesn't post content to your feed that is from people you follow, rather things that will make content go viral, I guess. From your perspective, are you suggesting that is harmful, or?
I guess I'm suggesting that it is like a algorithmic decision in a dynamical environment, and that we should think about how do we design that decision, right? I think, right, the main way these decisions are made now are you predict some measure that is considered good. The simplest one would be click, but actually I think social media companies do have more complicated objectives, like not just click, but also different types of commenting, different types of engagement, different types of longer term downstream behavior, session length, right? You try to model other things to try to make this smarter. But at the end of the day, you're still predicting some outcome and then just saying maximize that. Versus if you really want to think about underlying psychological state or harms, you should model the process with a little more care. And probably not just maximize a single score. Yeah. All right. Okay, so this is the end of this first part where I talk about some models, which honestly I don't think are true, but I do think help us think about phenomena that occur and maybe kickstart better algorithm design and better objectives. Now I want to talk about learning models like this. Learning dynamics models from bilinear observations, from the type of feedback that we would get in a recommender system. What would it take to start to identify these models rather than just assume some particular model is true? Okay. And I have until 40, is right? Cool. So here I want to describe the setting, which is motivated by the recommendation setting, so hopefully it won't take too long. I want to describe the algorithm and then do kind of a very high-level, informal setting of results, and also outline a couple challenges that we're currently working on. So our setting here is unknown dynamics and measurement functions. So we don't actually know exactly how a user behaves. But we do observe a trajectory of inputs and outputs. So, we have some inputs, which, for example, could represent attributes of a playlist that we recommend every day to a user, like their daily mix. And we have some outputs, which could, for example, be listen time. How much of the daily mix did a user listen to every day? But otherwise, we'll just abstract them to inputs and outputs. And I will mention the inputs here I'm modeling as multidimensional, right? These are like potentially high-dimensional characteristics of whatever our recommendations are. But the output for now, for simplicity, will just be a single variable. So it's sort of like one measure of affinity or engagement. The goal is to identify the dynamics and measurement models from data. And the actual setting that I'm going to study is the simplest one that I can think of that is appropriate to the recommendation setting, which is that the dynamics model of how the state updates is linear, whereas the observation model for how we see a user response is bilinear. And I've introduced like some unknown parameters to the setting. So A and B are the parameters of the linear dynamics. And C is now the parameter of the bilinear observations. And to get back at the question, this C allows some flexibility in exactly how the inputs are represented, U, and how the state would be represented, like its dimension, for example. Cool. And I'm going to have N is the state dimension, P is the input dimension, and 1 is the output dimension. And we have process noise, W, and measurement noise, V. Right, so this is a stochastic process, stochastic system. Okay, so that's the setting. And the question is, I would like to see this data, and I would like to find A, B, and C. Yeah.
A question about the dynamics. I was wondering if you could justify why the linear dynamics makes sense. So I think, you sort of made a good case for why the dynamics doesn't, or linear model doesn't make sense for the observations.
Yeah.
But why does that same sort of affinity-dependent effect not show up in the dynamics?
That's a good question. So I mean, there's certainly models where you would have nonlinearity there. Like I think nonlinear dynamics here are interesting. One answer, and I'm not sure how true this is because we model the state as sort of hidden, it could be a quite high-dimensional state, and so you could be kind of embedding some nonlinearities just like in the complicated state representation itself. But the more honest answer is just that if you can't do the linear case, I think there's no hope for the nonlinear case. And so at least building up the tools with linear dynamics will allow for slightly more complicated models down the line. But I think that there are some phenomena that I don't think can be modeled this way, but with a high enough state dimension, there's some things that you can model as well. But I think the bias assimilation, for example, I don't know how to model this in the linear case. So that would not be detected, let's say, by this method. Yeah. Okay, so how do we find these parameters? What's our identification algorithm? The input to the algorithm is the data, our trajectory, some history length L, that's a parameter that we choose at this point. I'll explain what it means, and then the state dimension. So I'm going to assume the underlying state dimension is sort of known for whatever reason, or guessed, or at least right now I'm not handling the problem that we don't actually necessarily know what that is. And so just remembering what our data looks like, we have inputs and outputs over time. The main step of this algorithm is regression. We're going to try to regress our outputs against past inputs, but past inputs in sort of a particular way, which is actually motivated by the structure of this problem. So we're regressing yt at time t, right, against the input at time t, transpose, so this is sort of like the bilinear part of the measurement model, right? So we would have to actually consider the response to the specific playlist that I recommended. But then we're also like regressing this in a product with a bunch of past inputs. So all the playlists I recommended over the past 2 weeks or something like that, right? So for some length L, and this is where our history length L is part of our algorithm. And solving this problem, this is a linear regression problem, we get some matrix G, is what I'm going to call it, G hat, which is sort of a matrix that, given some finite history of recommendations, predicts your response to the next recommendation. Also given the next recommendation, right? So this is the history of past playlists. This is the current recommendation, and then this is the response, right? And then if we really want to get parameters out, we can do a decomposition on this G into some estimated A, B, and C matrices, actually using kind of a classic system identification algorithm called the Ho-Kalman algorithm, which I'm mostly going to skip the details of for now. And this is the step where we actually need to know the state dimension, right? That's why I have it as an input. Cool. Any questions about this? Okay. So this is what we're going to do. The question is, does it work? And how certain or uncertain are we, right? At the end of the day, should we trust our estimates? Or, should we realize that our predictions are very uncertain and, do something to account for that? I'm actually not going to talk about the downstream problem for the most part, but I am motivated by the fact that uncertainty quantification is very useful traditionally in controls for safety, but I would say in the recommendation setting for like exploration, exploitation stuff. So like, what playlist should I recommend next? It helps if I know how uncertain I am about each of these outcomes. So let's move towards quantifying that uncertainty. So I want to talk about estimation error, and I'm primarily going to talk about the estimation error on this regression step, G hat, right, which we remember is some parameter that helps us predict the response from a bunch of past recommendations. And what it actually is, or one way to think about it, what I'll argue to you, is that this is an estimate, which is actually a little bit biased, of the Markov parameters of the system. Markov parameters are this matrix, so CB, measurement matrix, times input matrix, CAB, measurement dynamics input, and then increasing powers of A, all the way to L minus 1, so L total powers. These Markov parameters are mapping the effects of the input at various points in time on the state. So if you've ever worked with linear dynamical systems, this is something that you may have seen before, right? It's a map of how past inputs are affecting the state. And so without the C, it would be affecting the state. With the C, it's affecting the outputs. Okay, so that's sort of like, if G hat was perfect, we would actually estimate this directly. That's what I want to argue. So estimation errors will be in terms of the difference between G hat and G. So what's going on? Like, what is this algorithm? It's really just linear regression. So we can analyze it thinking about tools from linear regression. What are we regressing Y against? Something a little more complicated than normal. It's not just like against some X sub T, some covariates. Our covariates are actually this product between the input at time T and then the past inputs for the past L time steps. Right? And I'm going to call this history of inputs, history of playlist recommendations, let's say U bar. Right? So this is an expansion L steps in the past. So I can rewrite my regression problem that way. And then I just want to define the data matrix. So in linear regression, the kind of covariate, the matrix of covariates, or data matrix of all the features that we have, reading off my regression problem should just be a bunch of these vectors, right? U bar, Kronecker product, U. Okay, so I'm defining this matrix because it's going to be important for us. If I think of my past inputs U, and then I try to understand what's going on in this matrix, I have a bunch of U bars. These are sort of like a toplet or circulant matrix on these U. So the first set of U define this row, the next set define the next row, the next set define the next row, and so on. But that's not the end of the story. I also have a multiplication by each input itself, right? I have this kind of like at least second order term in the matrix. And that just gives me my U tilde. Okay. I wanted to spend a little bit of time on that because our results will be in terms of this matrix, and so are some of our open problems. Okay. So just to recall, G hat is our estimate that we use to eventually estimate A, B, and C. G are the true Markov parameters in terms of the actual A, B, and C. And U tilde is sort of like our data matrix in the regression problem. So our main results under some more or less justifiable assumptions. So we have stochastic process and measurement noise, IID, zero mean, and bounded second moments. The inputs are bounded, but we actually treat them as fixed. So given observed inputs, we state the result. And the dynamics we assume to be observable, controllable, and strictly stable, which means the spectral radius of A is less than 1. I know maybe not everybody here is the controls audience, but these are common words in controls and talks. So our informal theorem, first on Markov parameter estimation, is that with high probability, the error in our Markov parameter estimates, G minus G hat, measured in the ellipsoidal norm defined by the data matrix. So this is sort of like a data covariance matrix. The ellipsoid defined by my data covariance, measured in that norm, scales like two terms. The first one is our high probability term, which is like dimension over delta, the high probability, the failure probability, plus some constants that depend on the setting, including the stability of the dynamics as well as the noise, plus a term that comes from the bias of the estimation procedure, which actually scales with t, which is not something we normally like to see, but also decreases with L. So the longer we use our history length, this row of A is less than 1, the smaller this term will be. So if we choose L appropriately, we can make this term quite small. Although you'll notice we pay for L here. So this is sort of our estimation errors in the Markov parameters. And I have like 5 minutes left as of probably 4 minutes ago, so I'll keep moving. What about the system identification question of finding A, B, and C? Here, I can't make a guarantee about finding A, B, and C exactly, only up to some similarity transform. This is because of some inherent non-identifiability when you don't observe the state and only observe inputs and outputs. So that's why I'm writing this with some similarity transform S here. But the story is that actually the errors, the ellipsoidal errors here, scale with the errors on the Markov parameters with some constants that I'm hiding the details of right now. So as a summary, what this means is that roughly our estimation errors are scaling polynomially in dimension. And all of the results I just showed you were ellipsoidal norms on our data covariance matrix. So if I want to just translate that into just the pure estimation error in terms of like a 2 norm, an L2 norm, I guess Frobenius norm maybe, then I would pay the minimum singular value, 1 over the minimum singular value of that covariance matrix. So this is sort of our summary informal theorem. What's an open question is the sample complexity. So, right, given a bunch of inputs, I can say how well my estimation probably worked. But can I design a way to probe the user to recommend playlists that guarantee me to get small error in finite time? How large does t need to be to guarantee a bounded estimation error? So we have some conjectures here, but we don't have results. I think this is an interesting question. We think that random design, so choosing inputs at random, will cause the minimum singular value to scale with t. And that would give us kind of the type of identification result we would like to get. So, poly dimension over t. And in simulation, this seems to be true. It looks like this random matrix has this property. This is, by the way, a property that like a Gaussian random matrix would have or a pure circulant random matrix would have. But we haven't actually been able to come up with a proof for the particular matrix structure that we have, which is the product of a circulant matrix, which means there's lots of dependence between these rows, right? Like this entry is repeated, and a random matrix, which itself is correlated, right? So like this multiplication, I think, is the same as this into here. So lots of correlations in this matrix, so it's not something that we've been able to show. In conclusion, I think because I'm running over time, and I don't want to take up too much of the break, right, I talked a little bit about like preference dynamics as motivation, what do these models imply? And then I kind of switched topics to how would we learn these models from data? There's a bunch of open questions like sample complexity, relaxing a stability assumption, actually using these models to do predictions. So maybe we don't care about parameter estimation, just prediction. How do we use this to make recommendations and apply in different applications? So with that, thank you. These are all my collaborators. These are the papers that I talked about. And I take a question if we have a moment.